Well, hello, and welcome to Word Problems First. My name is Josh Britton. I'm the founder of Get More Math right now, but for 20 years, I was an Algebra 1 teacher in southeastern Pennsylvania. Our main topic is promoting conceptual strength through discovery in algebra. To kind of introduce the idea, I'm going to tell a little story, but first, quick apologies. I live right next to a busy road, so I'm doing this in the evening, hoping not too many milk trucks will roll by. And then also just, I'm sorry I can't see you in person. I designed this session to reach out to people in person. I love the dialogue and I will miss it, especially since I ask about 50 questions and I'll be doing a lot of sort of play acting to carry us through those parts, acting as if there were people in the room with me. Well, without any further ado, let's take a blast from the past. This goes back to one of my very first classes. It was called Intermediate Algebra. And I had, on the very first day, distributed a review worksheet to see what students knew from their prior year of Algebra 1. And the first problem looked like this. I still vividly remember the student who just had to explain to us when we reviewed the exercise how she answered this problem. She said, I know this one. You put your pencil here, you make a dot, then you rise 2, and you run 3. You make another dot. Oh, and then the best part, you connect the dots. And don't forget the little arrows at the end. Now, she was ecstatic. She loved to know how to do it and to be successful. And actually, as an early teacher, I was pretty happy too. Here, a student had retained the process absolutely step by step perfectly across the summer and into the next school year. Well, as the years went on, I began to realize there wasn't as much value in what she knew and could do as I thought that first year. In fact, in 2012, Pennsylvania introduced a brand new standardized statewide test, and I had a chance to look at the pilot questions and even give them to my students. The questions looked like this. I'll give you a moment just to read through this. Quite possibly, you're thinking, this is simple. But frankly, my students from my first years of teaching would have crashed and burned with a problem like this because I was all about steps and all about processes. And nowhere would my students, in the course of doing the big old thick book worth of problems that we worked through, have seen anything like this. The test makers in Pennsylvania had done a brilliant job of ensuring kids could think using the tools of algebra and not just repeat steps having identified specific types of problems. In the latter course of my career, I really began to think deeply about what do I really want for students? A bunch of processes or strength in understanding and the ability to wrestle with things mathematically? What's the point? What's algebra all about anyway? So this is where I would ask you, what's your definition? And of course, there are so many ways of trying to encapsulate it. But for this session, I'd like to suggest the following. Algebra could be, perhaps should be, a powerful journey from concrete math all the way over to abstractions for problem solving. Our students begin with the ability to work things out, to compute, and they end being able to identify patterns, build tools, and use those tools to solve problems. But there's a danger, and that danger is that we tend to start on the wrong side of the journey. So as a teacher, I've already taken the journey and I loved it. And I have now at my fingertips all these tools, powerful tools that I can use to encapsulate patterns, think through algebraic problems. And for me, it all makes sense and it's quite fast. Unfortunately, that's not taking into account my students and their needs. If we start by just shoving processes right at the kids, here's the process and here's how you can get the answer, We end up giving them things like rise over run or the slope formula, which probably for many people listening to this, you're like, what's wrong with that? There's nothing wrong with those things in and of themselves. But if we start with them, if we lead with them, we're likely to end up with what we so often hear from students. Oh, you want me to define algebra? Well, I'll tell you what algebra it is. It's a bunch of stuff that has X and Y in it. It's meaningless. It's useless. And I think that if students feel that way, it's because they haven't tasted the rich flavors of real algebra. They haven't had the opportunity to take the journey and experience the meaning. So this session is about how can we start at concrete math. And I called it word problems first because I'd like to suggest that instead of going right to processes, we want kids to think about mathematical situations. We want them to use some core concepts, explore situations, and gain then a whole different experience from algebra, a powerful journey where they are exploring and discovering the significance of patterns and algebraic tools. If we do that, the student takeaway could be very different. They're thinking about relationships. It's meaningful to them. And what I've seen when I've done it well is most of my students experienced it as very satisfying because they're using their brains to figure things out. Okay, well, let's then talk about this session and the schedule. I've broken it into two parts. First, I'd like to give you the same tiny little set of core concepts that I give my students near the beginning of the year. And just to let the cat out of the bag, it's all about pairs of numbers. So I'm going to actually sort of teach you minified lessons, the same lessons I gave to my students back in the day. Two, one about relationships and one about 3 ways to express them. Once we do that, once I give you these basic ideas that are sort of Josh speak for algebra, then we'll get to the meat of the thing. How can we foster student exploration with word problems first? And I'm going to give you 3 examples by actually trying to teach you 3 lessons. We'll see if I can fit this all in. I'm going to teach linear equations, systems of equations, and finally, a mystery topic. If I told you what it was, it would spoil the moment. All right, so let's start with relationships and the big question. This gets weird because, again, we're not in the same room, so I can't sort of treat you like the students quite. I'll do the best that I can. Let's see how this goes. So class, by the way, this is, see, I'm already getting mixed up. Side note, this is the first day of class and actually the first minute of class. I've already handed out seating charts. The kids have sat down, the bell's now ringing, and I say, well, welcome. My name is Mr. Britton, and this is algebra. Get out a piece of paper and write down today's essential question, which is, what is the main topic of algebra? Give them a moment. Well, let's talk about that. Oh, what a pretty picture. See the blue sky, lovely clouds. Oh, look at the bears. Aw, otters, penguins, halo players, holding hands. By now you're wondering, what class am I in? Is this algebra? Yes, because the main topic of algebra is relationships. So you can write that down. You already know the answer to today's essential question. What is the main topic of algebra? Essential answer is relationships. Now there's more to say. Wait a minute, relationships, really? Well, no, not that kind of relationship, but rather relationships between numbers. Which begs the question, how can numbers have relationships? They don't hold hands. Well, let's drill down to that. Here's our first algebraic relationship. Suppose someone gets a job delivering pizza. That person's going to work a certain number of hours and earn some money or dollars. That's our first relationship. It's a relationship between the hours worked and the dollars earned, a relationship between hours and dollars. Let's talk about this relationship, right? We care about dollars earned in particular. Unfortunately, in this relationship, there's one beginning part that's kind of sad. If your hours worked is 0, well, then your dollars earned is 0. But what about if we amp it a bit? What if somebody works for 1 hour delivering pizza? How much will that person earn? All right, so discussion ensues. Of course, I haven't told them, so they don't know. They tell that back to me. All right, well, let me give you a number. Say it's $8. Then you should be able to figure out this question. Suppose somebody in this same relationship works for 3 hours. How much money will that person earn? Discussion, discussion. Yeah, good. Well, what about 8 hours? Discussion, discussion. Okay. How'd you get that? Good. This is our first relationship. You see how it rolls. The more hours you work, the more money you get. And we all know that that's how it goes. Let's talk about a different relationship, another relationship between numbers, because remember, that's the main topic of algebra. This is what we're going to talk about for months. In this relationship, I'd like to talk about miles driven over against gallons of gas remaining in the car. And I'll get you started with this relationship between miles and gallons. When this car is in the driveway, it's got 12 gallons of gas. And I'll even take it a little further for you. The car goes 2 miles down the road, and now it has 11.9 gallons of gas. There is less gas. So as the miles are rolling by, the gas is getting burned. All right, if you've been really craving to get the math going, it's time. How would you figure out how many gallons will be remaining after 10 miles? Did you hear my question? I didn't ask how many gallons are remaining. I said, how would you figure that out? So I want you to talk to the person next to you. Okay, so we set up partners. It takes a little while. And they think about it and we discuss it and people have ideas. And I have a dry erase board, so I take wrong answers, right answers. But eventually we get back to, all right, so we determined it's 11.5 gallons. Let's do another one. How about 50 miles? Lots more miles, a little more discussion. People work it out. We get it faster this time. Okay, 9.5 gallons. Our second of many relationships between two numbers. Let's take it a little further. All right, so algebra is about relationships. What are relationships made of? Are you thinking conversation, time together, notes, gifts, inside jokes? Sorry, we're not talking about those kinds of relationships. We're talking about numeric relationships. So in our case, it's quite simple. Numerical relationships are made of one kind of thing. I'll give you some hints. We just saw a relationship where you work 0 hours, you get $0. You work 1 hour, you get $8, and so on. These, I want to give it away. These things in the middle of my screen, that's the stuff of relationships. That is what relationships are made of. In fact, in like math land, and you are now in math land, we usually write them like this. The first number would be, in our case, the hours, and the second number in our case would be the dollars. And I'll even give most of it to you. What are numerical relationships made of? Relationships are made of P of N. That's right, folks, P of N. Write that down. Any takers? Can you guess what those things are? Those three things in the middle of the screen? If you think you know, write it down on your dry erase board. A little bit of time. Yeah, pairs of numbers. Ooh, there it is. The magic, powerful core of what a relationship is. We are going to talk about pairs of numbers a lot. And quick aside for the session, we are going to talk about pairs of numbers a lot. So keep listening for those words. That's the essential kind of conceptual piece or tool or item that we're going to use to approach exploration of relational concepts. All right, back to the people in the classroom, the students. Finally, in algebra, we're going to answer a big question, and we're going to answer it many ways. And it's this, so you can write this down. As one number increases, write that down, give you a second, time passes. So as one number increases, the hours worked, maybe the miles driven, we always want to know, well, what do you think we want to know? Little discussion. I'll put it this way. What happens to the other number? You work more hours? What happens to dollars? You drive more miles? What happens to gallons remaining? So today we had an essential question. What's the main topic of algebra? And we said it's about relationships. What are relationships made of? Pairs of numbers. And the big question is, as one number increases, what happens to the other number? Great. Tomorrow, first thing, I'm going to ask these three questions, but on a piece of paper, and I'll expect you to know the answers. All right. So zooming back out, we're in a session, and I am kind of quickly skirting through some of the core concepts, the way I express some of the core ideas of algebra. What you just saw is almost verbatim, but more kid-friendly probably, and relational, if you will, the friendly kind of relational. What I do on the very first day, in the first 15 minutes, I have then some exercises where they have to identify the two kinds of relationships, some that cause where more of one number makes more of another one, and others where more of one number makes less of another one. They have to write some from their own lives. And there's things for them to do, but as I said before, this is a minification so that I can get to the meat of student exploration. All right. I wanted to share another core lesson to give you kind of time frame. This would be probably the fourth algebra lesson I give, where between the first one and this one, we've actually kind of stepped aside and done some coordinate plane work. And by the time those couple of lessons are done, where by lessons, I really mean exercises, explorations, et cetera, but no time to show those here, the kids can successfully graph pretty much any point at any scale, choosing scales. So if I say graph 378, 2, they can do that. And that's important to know as we get into this next piece. All right, so they've learned a little bit about relationships. We've done some stuff with coordinate plane, and then we say, okay, let's get back to the core idea of relationships. Lesson number 2, what are the 3 ways to show a relationship? All right, so we remember we're talking about numerical relationships, and we just reviewed in the warm-up that relationships is the main idea of algebra, and they're made of pairs of numbers, and we have a big question. Well, let's drill down a little bit. Review. If we have this job of pizza delivery for $8 an hour, going back to that example, what's the big question in this case? Take some time to write that down. Time passes, we go over it. Okay, good. The question is, as the hours increase, what happens to the dollars? And to answer that question, we're really going to need to talk about the stuff of relationships. Again, that's what? It's P of N? Yeah, pairs of numbers. Well, there are 3 essential ways to show pairs of numbers: the rule, the table, and the graph. Let's start with the table. And let's go right to the bad joke. Yeah, not that kind of table. Let's cross that off. What's a table? Well, in order to answer that, I need you to do some of the heavy lifting. I'm going to ask you 4 questions, and I would like you and your partner to answer those questions. So I'll give you a minute. Time passes, kids think, they respond. Yeah, good, right. So we put down our answers. All right. So let's just focus on the question and answer part that has the numbers. You know what those are really? 0 hours, $0, 2 hours, $16. Those are pairs of numbers. And we could express them in a table. How does that look like a table? I actually don't know why we call it a table, but we do. So there it is, rows and columns. Often we put at the top the meaning of the numbers. So the first column stands for hours, and the second column stands for dollars. But a lot of the time we use variables, where the first column we call it X, and the second column we call it Y. That, folks, is the first of 3 ways to show a relationship. A table gives you some examples of the pairs of numbers and the relationship. Let's talk about the rule. Going back to the questions you just answered, and don't worry, you don't have to answer them again. I have another question. Each of those questions, I gave you hours. What did you do over and over and over again to get the dollars? Discussion. Okay, what if I don't say hours and dollars? What if I say X and Y? To make it more clear, remember, X is often used to stand for the first number, and that Y is often used to stand for the second number. The rule is also the answer to that question. What did you do? What math can you do to the hours or X to get the dollars or Y? If you can answer that question in this form, you have expressed the rule. So what do you do to X to get Y? Yeah, okay, discussion. Got it. That's the rule. The dollars are 8 times the hours. You tell me some hours, I'll multiply by 8, and I'll get the dollars. So now we have the rule, we have the table, finally the graph. What's the graph all about? Well, we like to be able to say, give me a picture of every pair of numbers in the relationship, all of them, in a sense. Now, just real quick, how many pairs of numbers are in this relationship? Write it down on your dry erase board. Okay, those of you who said 4, hold on for a second because there's a couple more. I know the table shows 4, but the table just gives some examples. The graph is going to try to represent every pair of numbers. Now I've gone ahead and made a graph where the hours are the x-axis, counting by 3s, and the dollars the y-axis, counting by 20s. So now I'm going to actually plot some of those pairs of numbers, like 0, 0. Work 0 hours, get $0. Work 2 hours, get $16, and so on. And there's those 4 pairs of numbers. But couldn't you also work, say, 1 hour and get $8? Or 3 hours and get, the math, $24? Or 4 hours or 5 hours? And you could really sort of theoretically work 1,000 hours if you really put the time in over many, many months. The graph endeavors to show all of those pairs of numbers as points. Each point is one pair of numbers. Now, us math people, we like to keep it simple. We don't want to draw a bunch of dots, but instead we smooth it out with a ray, or in some cases, a line. But remember, when you see that ray, what you're really seeing is a whole bunch of points all connected together. So, today's lesson. To show numerical relationships, you need ways to express or talk about pairs of numbers. You have the rule, the table, the graph. The rule is like an equation. It tells you what to do to one number to get the other one. The table gives you some examples of pairs of numbers, and the graph gives you a picture of all of the pairs of numbers. Okay, zooming back out. Again, I gotta say that's very minified and rapid, but I'm trying to build a framework for you so that what we do in the rest of the session makes some sense. Okay, what can we do then? Going back to that idea of algebra being a powerful journey from concrete over to abstract, how can we foster that journey using, in particular, the kind of the tools and the language that we introduced in those first 2 lessons? Well, I'm going to give 3 examples. I'll keep doing it as if it were a lesson. And again, I will abbreviate a whole big period of time where like kids will be thinking, talking to their partners, talking to me. We're working on a dry erase board with sometimes the wrong answers, anyway. But I need to keep it trim. So let's go to linear equations. There are so many different lessons I do on linear equations, and I'm sure you do too. I thought I would choose this one because it brings out what I'm trying to talk about nicely. The essential question is, how are the table and the rule connected? All right, so, and I actually can't see the part of my screen that has the top part, but I think it says, suppose you There it is. Suppose you start with 40 bricks in a wall, and every hour you add 15 more bricks. All right. I have some questions for you, and I'd like you to take the time to answer them with your partner. So I'm just going to shut up, get out your dry erase board, work together, answer these questions. Okay, time passed, and then we discuss their answers, and then we summarize. Now, when you made that table, maybe you put hours and bricks, maybe you put X and Y. Either way is fine for me. I wonder if at the beginning, if you thought about what that really means, how many hours have passed at the beginning? 0, right? And then we said, after 1 hour, well, that's 15 more bricks, right? And after 2 hours, that's again 15 more bricks. So you figured it out. Great. Well, let's push this a little bit further. What do you think? Look carefully at the screen. What do you think the next question is going to be? Write it down on your board. All right, so we check. Somebody says something like, how many bricks are in the wall after 10 hours? All right, I've got a bonus question for you. I also want to know how you figure the answer out. So I want to know what goes where those question marks are, and I want to know how to think it through. Go ahead, work it out, and then what I really want you to do with your partner is talk about how you work it out. All right, let's bring it back. You know what? You answered 1 through 5 for me earlier. Why don't I do some of the work, right? Around here sometime. So I'm going to answer this one my favorite way. I'm going to thoughtfully and methodically figure out how many bricks there are after 10 hours. And you know what I'll do? I'm going to use the table. The table is a powerful tool. And I'm going to count my way through each hour. After 1 hour, I'm going to add 15 bricks. We've already seen this part, right? After 2 hours, I'm going to add 15 more bricks. After 3 hours, I'll add 15 more bricks. I think you get the pattern. After 4 hours, 5 hours, 6 hours, 7 hours, whoa, I'm just adding 15 again and again and again and again and again, and I get to 190. Is that how you did it? You know what? Don't tell me how you did it yet. Let's go to the next question. What do you think it's going to be this time? And actually, somebody just raised their hand. What do you think I'm about to ask you? Yes, I'm going to ask, how many bricks are in the wall after 50 hours? And how did you figure that out? So you go ahead, repeat process. Talk about what you think the number should be and how you figured it out. All right, time's up. Once again, I'm going to do the heavy lifting. And you know how I like to do it. I like to use a table. So I've made a table, and it's got 50 different hours to represent, or 51 really, if you start with 0. And I need to figure out how many bricks will there be at the very, very end of this. You know, some of you wanted to tell me before a different way of answering this question. Can we not do it the way I did it and go back and revisit what you were going to say? So you had a different way, some of you, I saw it on your boards. Let's talk about it, but actually talk about it with a different question in case somebody might not yet know this other way. Let me just ask you this. What was the increase in bricks altogether in 10 hours? In other words, you saw me adding bricks over and over and over and over again. How many bricks did I add altogether? And what are you going to do to figure that out? Go ahead, write down the answer on your own dry erase board and show me. How many bricks were added altogether? Yeah, and I see how you did that. That's good. You did 15. That's how many bricks you got in 1 hour, times 10, because 10 hours passed. So 15 times 10, or 150 bricks were added on. All right, what else do we have to take into account to get the total amount of bricks? Well, we already know it's 190. We talked about it. We see the answer on the screen. But what could we do to the 150? Right. That total of 150 that we're jumping from the beginning to 10 hours later, we would add 40 to it, and we get that answer. Now, we already saw that answer. But let's drill down to the middle of the screen. You can see there's kind of like a nifty little quick way of thinking this through. 15 bricks an hour times 10 hours added to the starting amount. I want to actually make that even more sort of condensed and mathy. I want to use the word expression. Do you know a way to write all the math we did, all the operations, if you will, in one little simple thing? Not doing the math, but showing the math that needs to be done. Can anyone do that? Write it on your board if you think you can. Okay. It's 15 times 10 plus 40. 15 times 10 plus 40 is the expression that will give us the 190. All right, well, let's go back to this question that I was like, oh my goodness, I don't really want to do this. And let's revisit this with the same pattern in mind. How about we just say, well, it's 50 hours. So 15 times 50. What next? Yeah, plus 40. So finally we get the 790. Do you see how easy that is? What would the math expression be that we would use to get that result? Try to write it down this time. See if you remember from the pattern last time. All right, it's 15 times 50 to get the total amount of bricks that you increase by. Add that to the starting amount and you'll get your total. All right, well, I have 3 more questions for you. It's back to you and your partner. I'm going to shut up and give you a few minutes. Okay, time's up. And then we discuss, and we come up with these answers. So what math will you do to fill in the table? Notice I didn't ask the answer. I just said, what math are you going to do? Well, it's going to be 15 bricks an hour times 800 hours added to the 40 that you started with. And just in general, if I tell you hours, what math do you do to get bricks? You multiply the hours by 15 and add 40. And finally, if instead of saying hours and bricks, I say X and Y, what are you going to do? Well, I'm going to cheat a little bit and add something that we haven't been seeing. But the bricks, which is Y, the bricks will be equal to, and then here's the thing you might have written, 15, that's bricks per hour, times the hours. Now, I don't know how many hours it is this time, 10, 50, 800, that added to 40. Do you recognize that from a lesson a while ago? What do we call it when we have an equation that tells what to do to X to get Y? We call this the rule. So we just played around a bunch with numbers and came up with the rule that governs this relationship. Let's practice that same kind of thing with some other problems. So go ahead, read this problem, fill in the table, and then answer the last question. I'll give you a minute. Okay, time's up. Talk about it some, maybe do it on the dry erase board, then put it up to make sure we have it right. We go through it maybe on the slides. This is me just talking to all of you at this session now. Okay. So the students come up with the rule or equation. We talk about using Y equals, get the pattern, use the pattern, etc. I love this problem. And I've been racing along. I want you to read it. Think for a minute. By now, the kids are just like, oh, we got this, right? And a bunch of them actually don't read the words. They have the habit, because the brain is brilliant at coming up with processes and sort of jumping to abstractions and then stop paying attention to the thing itself. So the kids will say, they'll say, it started with 210, and they'll see that 6 and they'll put in a 216. So when we review this is always kind of an explosive moment, if you will. I stop right here and I ask, what should go here? And they'll put in often, they'll say 216. And then we'll talk about, well, if you explode a thing, then it's gone. You don't have it anymore. And if she's exploding 6 of them, 6 more are gone. You don't have 6 more of them, you have 6 fewer. So at some point somebody will say, well, what's a Kent anyway? And I'll say, does it matter? If you explode them, are they gone? So a whole nother conversation as to why sometimes I use nonsense words, different session. But anyway, Over time, then we go through this and we talk, then this is kind of a twist, right? All of a sudden there's this change and the increase in X causes a decrease in Y. We have a discussion about that too. This is interesting because a lot of the times when I ask for a rule, they do a great job with it. And it's very common for them to pattern it, 210, take away something, 200, that's the way people think. So that's the rule really, is 210 take away 6 times the number of hours. And then I feel obligated to sort of prepare us for the future. I say, all of us math geeks, we do it this way. I don't care which way you do it, but that's how you'll see it as you move forward. Okay, so that whole lesson, lightning quick, zoomy, was to try to give you a cursory sense, at least, of how using the building blocks of algebra and starting in the concrete can kind of inch you towards the abstract and give the students the chance to have the journey and to think about the pairs of numbers. Instead of, by the way, what would the contrast be? Well, I don't have time for what I used to do, but this is y equals mx plus b. M is the slope, b is the y-intercept. Here's what you do with m, here's what you do with b, it's just abstracted from the get-go. And we don't get to abstract until they get to abstract. All right, well, let's reboot systems of equations. So once again, we're gonna have an essential question, and I'm gonna try to model taking the kids on the journey from concrete to abstract, giving them a chance to really wrestle with concepts instead of just dumping the final results on them. All right, so hey, today's lesson is, what is system of equations? To get to it, I'm going to offer you a job. I have some work to do on my property, and it's going to take days and days of work. So I'm going to pay you $50 every day. What would the rule be if y is dollars and x is days? Write that down. Good. Oh, you know what? There's another possibility. If you really want to invest in this, I'll tell you what. If you pay me for the privilege of working for me, $200, then I'll pay you over time, over the days that ensue, $100 a day. What would that rule look like? You invest $200, you give $200 to me, but then I pay you $100 a day. Talk about it, look around. Good. Okay, I'm going to let you choose. Do you want me to pay you $50 a day or $100 a day, but you have to pay me $200 at the outset? I'd like you and your partner to decide which of those two rules is better. And to do that, I want to see on your dry erase boards 2 tables, each of which has at least 6 pairs of numbers. Ready? Go. Okay, time's up. So we go over the tables. They give me pairs of numbers. We talk it through. I actually ask them what they think. Usually the students I work with, and I don't think I mentioned this, are kids who often have a history of struggling in math before they get to high school. They'll have an opinion, the first one, the second one. But some kids will say, well, I'm not sure. It kind of depends. And that's the beautiful piece, because they've really thought about it. So we go through and we talk about how at the beginning, the $50 an hour is better. But then at the end, or not in the middle, but after 4 days, did I say an hour? I'm sorry. I'm starting to get mixed up. After 4 days, the $200 is the same. It doesn't matter which rule you use. And then after that, it'd actually be better, even though it costs $200 to get things started, it'd actually be better to get the rule with $100 a day. So this is what they kind of did. We talk it through and they decide. The final answer that we come to is, well, the answer is it depends. If you work fewer than 4 hours, you want $50 an hour. If you work more than 4 hours, you want the $100 an hour with a $200 investment. And if you work 4 hours, doesn't matter. All right. Then I ask the question again. I say, okay, you already answered the question. You know the answer now. I want you to answer it again. I'm going to give you some time to work on it. I want you to make 2 rays on one grid where each ray is for one of these relationships to show how they perform over time to answer the question that we've already answered again. Ready? Okay, time's up. And then we talk it through again. And I ask them questions like, what does this point represent? And they'll say something like the pair of numbers, or I'll say, what does it mean? Well, means that if you don't work at all, then you're down $200 because you had to pay $200 to get the job. And we'll talk about this point. It means if you don't work at all, you don't get any money. And we'll kind of work our way through the points. And this is, of course, preparatory to a later lesson when we're actually solving systems using graphing, but it's more for a discussion point. All right. Okay, everybody. Remember the essential question? We've been working on it now for 25 minutes. What is a system of equations? This right here, the stuff I just put on the screen, that's a system of equations. It's two or more rules. In this class, usually it'll be two. All right, there's another piece to systems of equations that I'd like to introduce. And actually, depending on the length of the class, this could sort of the beginning of the second lesson. And that's, what is a solution? In a system of equations, we talk about a solution, and it's a particular pair of numbers. In the one we talked about, it's the pair of numbers 4, 200. That's the pair of numbers that is in what? Blank relationships. Right. The pair of numbers that's in both relationships. Now, we are going to spend quite a bit of time finding solutions of systems of equations. We'll want to know what pair of numbers is in both relationships. So let's get that party started with this. Mr. Britton hosted a skate competition in his backyard. He charged $2 for red tickets, we'll call that X tickets, and $5 for blue tickets, we'll call that Y tickets. He made $90. Please write a rule for this relationship in standard form. Kids do it, we check, good. All right, why don't you fill in a table with some pairs of numbers in that relationship? Be sure to include the intercepts. Those are all prior skills. We didn't see that lesson. So kids do that. I say, well, let me turn this into a system of equations. What will I need for that? Right, another equation. Well, here's another sentence. Mr. Britton sold 30 tickets. Just focusing on the purple words, what standard form equation could you come up for with that? Again, this is a review for them. They come up with this. Okay, once again, give me some pairs of numbers. Make sure you have the intercepts included there. They do that. What is this? Again, it's a system. And what we're going to want to know a lot of the time is the answers to questions like this. How many red tickets did he sell? And how many blue tickets did he sell? We know he made $90. And we know he sold 30 tickets. What pair of numbers meets both of those requirements? What pair of numbers is a solution to each of those equations? What pair of numbers is in both relationships? And how can you figure it out? Well, as I said, we're going to spend a lot of time talking about how to figure it out. But the sort of basic, straight up beginning way of doing it is what we call guess and check. And it is just what it sounds like. So you and your partner work for a while to find a pair of numbers that adds up to 30 and makes $90 for Mr. Britton. Okay, time's up. Kids figure it out. They mess around with numbers and figure it out. Because by this time in the class, they're used to playing with numbers, plugging things in. You know, I might go over the dry erase board and I might help some kids with guesses. We're all processing. So one kids find it, another pair of kids will find it. It's really fun. All right, let's do another one. Read the problem. You see it says system there. I want a system of statements. Everybody on your dry erase boards, write the system out, the two equations. So they do And then I say, well, what we're often going to want to know is what's the solution? What pair of numbers adds to 34 and also comes to a total cost of 144? So you already know the strategy of guessing and checking, but a lot of the time when I ask these questions, I'm going to just have you check. So let's take off the guess part. I'm going to give you some possibilities. And then you decide which of these pair of numbers could actually be the solution. Which one is in both tables? Well, let's just start on checking this one. Don't worry about all of them. Is that a pair of numbers in both relationships? Work it out. Okay. Discussion, we talk about it. So we talk through what makes a pair of numbers work. You have to plug it in, see if it's a pair of numbers that works in that relationship. So this is the checking part. This one checks here, but doesn't check there. This one checks there, but doesn't check there. And finally, this one checks for both of them. Okay, we'll finally get to the mystery topic to conclude. Remember, my goal is just to give you a sense of how you could start with some concepts and use those to foster that powerful journey from the concrete to the abstract. And my focus is on using word problems and the notion of pairs of numbers. And in this mystery topic, this is one of my favorites. And in the 10 minutes I have remaining or so, we will address this essential question: what is a blank? All right. To get to today's question, I want to do a little bit of setup, a little bit of review. So suppose you're going to buy 3 bags of chips, and they're $2 per bag. What math would you do to find the total cost? Don't tell me the total cost. Tell me the math to do. Good. Let's say chips aren't enough, so you decide to buy 4 subs too. They're $5 each. Again, what math would you do to find the cost for the subs? Don't tell me the total, just tell me the math. Right. So the total cost would be from adding those together. Continuing our review. Suppose I actually don't tell you how many bags of chips we're going to get. Let's call it X because we don't know. You can still tell me what math would you do to find the total cost for the bags of chips. Good, that's right. And what math would you do if you knew it was $5 per sub, but you didn't know how many subs would be purchased? Call that mystery number Y. Good, yes, it would be $5 times the number of subs, which we don't know. Add them together, you get your total cost. Okay, I hope you're thinking, yeah, we basically just reviewed standard form. All right, well, let's carry it on to get to our mystery topic. Not there yet. Let me add an element. Suppose I tell you you have a $10 bill and a $5 bill. You're going into the store. Chips are, which we'll represent with X, are $2 a bag, and subs are represented by Y and $5 a bag. So you have those $15 to spend. It's the usual, people. You've done this for months now. Give me the pairs of numbers that show you what you could buy. We'll get to the mystery topic in a moment. You fill in the table. You give me every pair of numbers showing what you could buy, and I'll get a drink. By the way, this is partner work, please. All right, session people. This particular exercise, I'm walking around the room, and within a minute or two, I have several happy, content, done kids, and they just have like 2 pairs of numbers or 3 pairs of numbers on their boards. And I just walk around. I don't say anything. I smile at them. They smile at me. And then almost always, there's that group that says, hey, Mr. Britton, we have a question. And I go over and they say, do we have to spend all our money? And I'm like, I don't think you have to spend all your money when you go into a store. Yeah, I don't think so. And they're like, oh, okay, thanks. And they methodically keep going and come up with tons of pairs of numbers. And so I let that go for another minute or so. So now like 3 or 4 minutes have passed. It's painful. There've been kids that have been done for forever, right? And I say, if you only have a couple pairs of numbers, just so you know, there are 18 pairs of numbers in the complete table, and I want all of them. And there's this kind of ripple through the room, like people looking at each other like, wait, what? And the realization starts to dawn, and they start to figure out, oh, we don't have to spend our money. So it rolls differently every time, but it's a really meaningful moment. And it gets to the core of what this session is about, getting kids to actually think about the relationships, to think about and grasp in a concrete way the power of the pairs of numbers that are in the relationships. So that's a fun exercise. In the end, then they share, we talk about, we come up with this huge list. And then I say, okay, here are my tables, but I actually have 2 pairs of numbers that are hidden in there that don't work. And then I have them figure out what they are. There's 2 pairs of numbers that are not possible. So they talk about it, they figure it out. We talk about why. We do the math. How much would this cost? How much would this cost? You don't have enough money to buy a bag of chips and 3 subs, or 4 bags of chips and 2 subs. Okay, so here's the complete table. Here's every pair of numbers that's in the relationship. Let's talk about the rule. What's the rule for this relationship? We've been doing rules for months. We usually just put a big old equals there and call it a day. But equals means equals. It means spending $15. We can't use it. We don't have to spend all the money. So what can we put there? Does anybody have an idea? So then we have a little discussion. Sometimes it goes a little further. Sometimes it doesn't go very far. All right, well, let me give it away. What's that thing called? Sometimes they know, sometimes they don't. We discuss it. That's a less than or equal to. Less than or equal to. So finally, we can get to today's essential question. What is a linear inequality? That symbol we just used is an inequality. So we used to use equals, but now we'll be using inequalities because equals won't quite cut it, although it's helpful. Now, this next piece of notes is optional. If you forget and you need to learn this again, these 2 symbols can get confusing. The first one is less than or equal to, and the next one is greater than or equal to. Write that down if you need to. Okay, so basically what we just did is we did this situation. I'm going to really zoom because I want to get everybody in the session to my last little bit before I run out of time. So I'm actually going to kind of cheat a little bit because we kind of talked about this. I have them work through questions like, give me a pair of numbers that works, give me a pair of numbers that doesn't work. Finally, we get to graphing. And this is how I kind of want to land this session. I put this screen up. We're a couple months into my algebra class. This is our first graphing of any linear inequality ever. The directions are on the screen, and I say to my kids, follow the directions. And then I start walking around. It's beautiful. It's incredible. They start to graph on the dry erase boards. They label their axes and they start to put down dots. They'll make a point at 0, 0 because they understand that means 0 chips and 0 subs. They make a point at 0, 1 because you could buy no chips and 1 sub, or 0, 2 or 0, 3. And they laboriously, methodically work their way through every pair of numbers in the relationship. The reason this is beautiful is because I never had to say, there's a shaded region, choose a shading side, or choose a test point, plug it in. If it works, shade that side. If it doesn't, shade the other side. And you know all that stuff? I used to teach that, and my kids got so confused, didn't know what it meant, never even mind systems of linear inequalities. My students knew exactly what they were doing. They grasped the concrete meaning of this abstracted rule and they could represent it graphically. I want to go back to this problem. When I first saw problems like this as earlier in my career, I was dismayed, but really it was a good wake-up call. And I thank the people at the Pennsylvania Department of Education who make such a quality standardized test here in Pennsylvania. For them, it's not about just a bunch of steps. It's about kids thinking mathematically. It's not just training kids to go through process. It's about carrying kids along that powerful journey from concrete to abstractions. Thanks so much for your time. I really appreciate your willingness to check out some other ideas. I hope it's been helpful. Again, my name is Josh Britton. I'm the CEO and founder of Get More Math. If you have questions or you want to talk further, I've put my email here on this last slide, and I would love your feedback. All right, all the best.